Hello everybody, today we will be working on an older no-name SD card. It's only 2 GB in size, so the job should be fairly quick. There's the label. As you can see, this is a generic card with no name on it, and it even has a glued up controller. Usually this is not something new for devices similar to this. No brand names often do resort to these kinds of builds, but let's test the card out because I haven't really played around with it yet. Best thing would be to check the interface and see what comes back from the controller communication. So for that I use PC3000 together with the adapter for the cards, and here we can plug in the card directly into the socket. This adapter has a very useful functionality in the utility that we can work using different protocols: SD, ISP, MMC, and in this case we're going to try to power up the device using SD protocols. Standard operation to see what we get back as a result. So right off the get-go, I see that it's hesitating to get recognized. Now, what I would normally do, I would remove memory chip from a device like that and test the card again to see if the issue is still there. So for that, we're going to put the card in the jig, clamp it down, and apply a little bit of flux on both sides to take the memory component out. So a little bit here. The work will be done with removal using hot air station. I usually use 365 at 40% airflow. So once we have the removed memory chip, we just need to make sure that the connections on headers are all clean. Usually there's going to be some flux residue that needs to be brushed off. Now that the memory chip is extracted and cleaned, we can place it in the reader and attempt to read the raw data out of it. For that, I have a socket that looks like this. If we look at it in the microscope, you guys can see that it's got clamps on both sides, specifically for this type of component. This arrow right here indicates positioning of the first pin, and the dot on the chip indicates the same. So all we gotta do is just drop the chip inside, line it up, and clamp it down. Now we can connect it to PC3000. PC3000 unit, when it's connected, it will allow us to power up the software that we will use to reassemble, or should I say assemble, a logical image of the device. We're just gonna call it PC3000 controller. We don't know what controller this is, but what we do know is that there are some markings on the PCB, and that's what we're going to use for referencing this. So if we look here, it says PBM85SD-C. I'm going to write that down. And while we're in a task, first thing we do is we confirm that the chip is readable. So we're going to obtain the chip ID from it, and if we get the ID, we can see what data looks like to make sure we don't have any reset delays or anything like that that will change how the device looks like binary. If we go into read chip and direct mode, it will be able to read the chip on the fly. And if we go into page designer from here, selecting bit view will show us what the device looks like. First thing to note, if this device had XOR, we would not see these lines. These horizontal lines indicate most likely that there is no XOR present. The data should always look like this. Well, unless it's pattern of some sort, like a file table or something. In this case, this is what normally the data would look like, and if we got these horizontal lines going across, that tells us one thing, and that one thing means that XOR is not present, because if the XOR was present, everything would look like this. XOR on top of zeros will make it look like a pattern, but when you mix it up with actual data, that pattern will be very, very hard to notice. So I don't know what these lines mean, but we're gonna find out. The fact that we see them indicate that most likely no XOR present. So if we get lucky, maybe we'll stumble upon a table, something that will just confirm that this is not a XOR device, but we're doing it in a direct mode. So we're gonna clear it for now, and we're gonna go ahead and read the chip into a dump file. This will basically create a binary file inside of the task folder that will just save everything from the chip with default parameters that are already stored in the database of the tool, and allow us to manipulate that file later on. We can basically replicate the function of the controller without the physical controller being present, right? So inside of the memory, we have data in a physical image form. So it's what the data is made out of. I brought this analogy many times on this channel, and that's what I always tell to my clients when it comes down to explaining how NAND recovery works simply. It's very similar to putting a puzzle together. When you're putting a puzzle together, you're dealing with several steps. Step number one is you go to the store, you get a puzzle box. All the chips are inside of this box, right? So that box with chips inside is what the NAND is for this data recovery case. The NAND is the box, technically, and inside of that box we have chips, and those chips are bits of data that are all tossed around and mixed up, and they need to be properly organized and assembled in a specific sequence, like the puzzle maker had intended, in order for us to see the picture. We're not going to see any files until the logical image is built. Now the logical image is going to be built, but first we need to determine what it consists of, what the function of the controller consists of. So different controllers operate differently, different memory chips are structured differently. There are some chips that read well, there are some chips that read extremely bad, there are some chips that read only under certain commands, there are certain chips that read excellent at the very first run. This being such an old device, and how clean the service area looked, even in the direct read view, I can tell that there's going to be very minimal to almost no error correction needed, because chances are this memory is very, very stable. And looking at how the preview was representing it, I can say that most likely the device died not because of the NAND, but because of something else, and most likely the controller itself. Most of the time, cards, memory cards like this, if you remove the memory from them, they will not be busy anymore when they're trying to load. So I've showed this several times on this channel already. When you remove memory from a flash device, most of the time it will drop into safe mode, ROM mode, whatever you call it, and controller will present its own version of environment. Like, so it's gonna get ID'd, but it's gonna get ID'd with a specific size that doesn't normally correspond with the actual size of the device. It's either gonna be displaying something very, very tiny, or like completely out of line. So like, for example, a few videos ago I posted an episode about SanDisk cards, and the reason why they get recognized as 30 something megabytes instead of the actual size when they go bad. Recently I posted a video about Lexar and why that Lexar memory cards would get recognized as 7.61 gigabytes instead of the actual size. So normally good controllers, they will provide some sort of feedback to the interface if the NAND is disconnected. It kind of gives them a relief, and they can show up. But if we remove the NAND and our card still hesitates to mount, still hesitates to load an ID, then the problem most likely is somewhere along the circuitry. Either the circuit board is damaged or the controller is damaged. So we're almost done reading, and the reading of this device is a fundamental step. Now that we have our transformation graph formed, we can go into Page Designer, and now it will not hesitate at all when we're scrolling through, because it doesn't have to read it first to display it. It already is read. Let's go and find ECC first. ECC is going to determine what our ranges are, and from those ranges we can make an assumption that based on what I see here, it looks like a SAM controller, because we got big range first and then the rest are following small. This is something interesting because the last one is also big, but that might be just because it's an old device. Who knows? I'm gonna run ECC right now. It's gonna run fairly quick because again, it's a small device, and as you can see, most of these are green. Not most of them, but so far all of them that I see are running green. So the memory is in extremely clean state, and when we build the mix that this controller is using, I have no doubts that we're gonna get close to all of the data that was on this device originally. And as you can see, it's almost at 50%. To test whether or not this device has inversion, because of how the bit view looks like, it's fairly simple. If we run raw recovery on a device that doesn't have XOR, it's going to start coming across some shreds of data. Whether they're going to be working files or not, that's irrelevant at this point, but if we run raw recovery, it should come up with at least something. Text files, traces of pictures, PDF files, whatever was stored on there, shreds of those files should come up. So we're running it and we see we're not seeing anything come up in raw recovery right now. So what does that tell me? It tells me that most likely this unit is using inversion. So we're gonna go and apply that element, bitwise inversion, to invert user area and potentially service area. We're gonna have to test that. I'm not sure if we need to do it here, but on some devices inversion only applies to data area. So now once we click on that inversion element, we're gonna run raw recovery on that as well, and right away you guys see that it's coming across JPEG images, because this is obviously a memory card that was used in the camera. The fact that they're all red just tells us that they're not complete yet. They're not properly assembled yet, and that could be due to several things. First of all, we need to arrange our page structure, and we need to figure out if there's any mix. This is again an older card. We don't know what specific controller it carries yet, because we can't run XOR validation. We can't just assume that it's something, because nothing is written in regards to the controller on the PCB. If we go into tools and ECC and view our ECC information just to refresh our memory, it gives us these ranges. So because there's a number of them, I need to calculate them, like add them up. I mean 1 2 3 4 5 6 7 8 9 10 11 12 13 14 of these and 2 of these. So I have always a note file available to write the stuff down, so that we don't have to go back and forth every time. So 539 is our first range. Then we got 14 ranges of 535, and then we got last range 539 again. So we're gonna go into calculator, I'm gonna type in 14 times 535. This is the value we get. And now we can go into Page Designer and actually split it up. So first one is gonna be 539, and this one is going to be 7490, and the last one is gonna be 539 again. Now this one we can split now proportionately because we know there's 14 of them. Now we select them all and we cut the data part out. The data part is 512. We add this to our sector. We add this as a marker. Done. So now we're gonna save it, and this will apply a page transformation element to our transformation graph. Now we have this here. If we go in and view it through bit view, it will have everything nicely spaced and ending right where it needs to end. As you can see, this is like super clean. We don't have any dots inside of the solid colors. Everything is nice and beautiful. So what usually happens after things like that, especially on older controllers, we're gonna have elements such as block pair, and it's easy to determine whether the block pair is present by simply going into split by block element selection. And when we have them set up here side by side, select them both and do comparison. If our service areas look the same, then there's a good chance that we need to pair them. But from what I see here, they don't look the same at all. We have 64, we have 68, we have 3C, we have 3C here. That's kind of similar, but they look different further out. And here they don't look the same either. So there's no interleave. So we can delete this element, and to test how our mix is doing, we can run raw recovery, because we know that there's no interleave. So interleave will break things up into quite small chunks. So if the interleave is needed, without interleave, raw recovery is not going to come up with much. But if the interleave is not needed, then we're going to get healthy images as it is. So we're going to run this, and I see still there's a lot of red images coming through, but there's also a lot of green images coming through. Keep in mind that memory cards, especially when you're working on recovering a card that was used in the camera, they don't always have filled up capacity with working files in them. So some cards will only be filled up to 25%. But that doesn't mean that the card was not extended and used to its entire space before. So if it has been, old files will still remain on the card. And that's maybe something what we're seeing here as red highlighted files. If the files had been previously taken by this camera, but then the camera was formatted, and on fresh format new pictures were taken, these new pictures most likely are appearing as green. As you can see, if we go into map our ECC map, if we select invalid sectors, it will show us how many sectors we need to still reread because they couldn't be corrected. And we have nothing here. So that means everything has been corrected and everything is accounted for. So if we go back, we see these black ones. Black ones mean sector is invalid or empty, I'm sorry. So if we create selected valid sectors and corrected sectors only, we see that 1.87 out of this whole space belongs to that. So this is all corrected and good data. I don't know how to select these black sectors, but they have nothing in them. Let's assemble the logical image. From what it looks like here, actually, let me just check something. we looked at the headers, but we didn't really actually check if the files had been if the files are opening up or not. We're looking at this capacity at this column here. It shows us that the resolution is 2048 by 1536, and that's the resolution for the file. It's fairly big, so if it works, that means our pictures are good, and if the pictures are good, the mix is assembled correctly, even though there is technically no mix, there's just inversion. Probably somebody wants to restore their old precious memories. If somebody gave me a card and said, Erkan, here's the card from when you were a kid, having things like that, if you have an old card laying around somewhere that you haven't seen from your childhood, I mean, it's gonna be an amazing thing to go through it again and see those images. Sadly, I don't have these cards from my childhood. We actually didn't have cards, and when I was a kid, we had these, I don't know what are they called, cartridge rolls. So it's like, you know, these things that they roll up for the negatives, and then you have to print them. Those are the cameras we had, and I don't know where the negatives are at this point. Definitely not in my possession. Anyways, so let's go ahead and build this thing up. So this is a older device. I don't know if there is a specific controller for that, because we don't know what that controller is. So we're just gonna go to default method, which is block number type 1. And just going off of this general information, the address for our marker position located in the first range starts at 512, because it's gonna go 511 will be the last bit for the data, and 512 because the count starts from 0 counts as 1, and 512 will be the start, so technically it's 513th in sequence. I remember that with inversion, the mask that we would use is 03FF, and marker position is good, block size for us is good, everything else looks good. So let's go ahead and build this block number sequence. So once the block number sequence is built, we should be able to see the file system. And if we open it up, we see that the file system gives us a name. No name is still a name, and there is the root. So yeah, let me know, guys, if you have these old cards. I think what I'll do is I'll do something special for this episode. I usually don't do this. If you have a memory card laying around at home, let's just say less than 16 gigs in size, with your childhood memories on it that you want to get back, I'm gonna post a comment which I'm gonna pin right underneath this video, and if there is enough interest, I mean, I don't expect hundreds and hundreds of people to submit their interests on that, like I don't get that many views, but if you have a card that's less than 16 gigs from your childhood memories, and you wanna see that footage again, hopefully it's just photos, and I assume it would be photos if it's old, I will do this gesture for Christmas. I'll take on 3 cards. So first 3 people who will comment that they got a 16 gig device or smaller with their childhood pictures or something along those lines, I will be happy to help you guys out and do this Christmas giveaway. So no charge, obviously. Obviously no charge for those first 3 who submit. And then on my Instagram, the handle is right on the screen. Just send me a DM, tell me that you replied to that comment, and like I said, first 3 who post on underneath the video, I'll do it up. But you need to have a card. I mean, don't post if you don't have a card. Don't, just not to throw others off. If you have a card that you want to recover, it has to be 16 gigs or less. Let me know, and I'll do what I can to help. So we're here, guys. We're finally here on the last stretch of things. We got DCIM folder. That's beautiful. We got our subdirectory here. Great. Let's open up a file and bam, it works. So now we're just gonna go ahead, select it and hit save. Thank you guys for watching. I really appreciate it. If you're new to the channel, don't forget to subscribe. If you like this video, hit thumbs up. It really helps to get these videos out there on YouTube's. And yeah, as always, if you got a device that you need to recover, slide into description box. There is a link to our website where you can grab our services and we will help you out. Thank you very much. I'll see you all in the next episode.